Hi everyone. So till now we have studied vector algebra, coordinate system, vector calculus, and then we studied Maxwell's equation and EM wave. Now we are going to start transmission line, a very important chapter and a very easy chapter as well. If you have studied EM wave, this will be a cakewalk for you. You will feel like that this is very easy. Okay. So we will go to the transmission line. We will understand what is the meaning of transmission line. Why do we study that? But before that, we will see some basic concept of network analysis. Okay. So we will go to the topic, but before that we need to have patience and understand some basic things. Okay, so I am asking you a very simple question. This is a 3 volt battery, this is a resistance R. I am closing the switch at t equals to 0. Just as I close the switch, what will be the potential at point A, B and C, and what will be the current passing through these nodes? So just as I close the switch, in network analysis what do we study? Just as I close this switch, this 3 volt will be going there. So VA will be equals to VB will be equals to VC, that will be equals to 3 volt at t equals to 0 plus only, right? Just as you close the switch, 3 volt was going there, and what will be the current? The current will also be from IA, you can say IB is equals to IC. The current will also be 3 by R. So just as you close the switch, 3 volt has reached here. Now no matter how much long line is there, if I ask you this question in network analysis, that just as you close the switch, what will be the potential here? You will say that sir, just as you close the switch, 3 volt reaches here. But does this happen in real life? So let's check that out. Okay, this is what we have studied in network analysis. But what if this is a wire I am taking, the length of the wire is L. Okay, 2 wires I am taking, length of the 2 wires are L. At one end I am connecting a load. This is a load I have connected, ZL load, and this is my source. Okay, this is my source. I am applying a source, and the switch I am closing at t equals to 0. This is your source. Your source is Vs is equals to V naught cos omega t. This is your source. What is your omega there? Omega is 2 pi f. And what is the value of f? 1 gigahertz. And the length of the transmission, the length of the line, forget about the transmission line, just length of this wire, I am assuming to be 3 centimeter. Okay. And now what will happen is that just as I close this switch, this Vs potential will go towards this line, right? This Vs potential will start working. So this Vs potential is working with the speed of light. This is what I am saying. Okay, it could be anything. I am just assuming that between the two wire, there is in between air. Between the two wire, if there is air, that means this wave will travel. This voltage wave will travel with the speed of light, right? Okay. So just as I close the switch, what will happen? Here this V naught potential will come. Just as you close the switch, here V naught potential will come. Now there is something that I defined called as transit time. That transit time is equals to L by Vp. Basically, to cover this distance L, how much time will be required for this voltage wave? For this voltage wave to cover this distance L, how much time it will be requiring? So distance upon time. So that would be 3 centimeter means 3 into 10 to the power minus 2 divided by 3 into 10 to the power 8. So 10 to the power minus 10. So what we are getting, 3 into 10 to the power minus 2, this will be 10 to the power minus 10. So it would be 0.10 to the power minus 10. So 0.1 nanosecond. Okay, just a second. Yeah, so let's make a change. Let's take this length as 3 meter. Otherwise, this will not make any sense. I am taking this length as 3 meter. So if I take this length as 3 meter, then what will be the calculation? How much time it will take? 3 divided by 3 upon 3 divided by 3 into 10 power 8. So this will be 10 nanosecond. So transit time will be 10 nanosecond. That means it will take 10 nanosecond of time for this V naught to reach here. Are you able to understand this point? Just as you close this switch, this V naught will start traveling. This peak will start traveling, and it will take 10 nanosecond time to reach here. Is that clear to you? Right? So previously what did we say? That immediately 3 volt will come. But here if I analyze, I took a wire of length L and the length was 3 meter. The velocity, maximum velocity could be 3 into 10 power 8. If there is air in between. If there is some other dielectric, then velocity will change. That we will see. Okay. So maximum velocity I could take 3 into 10 power 8. What is the transit time we are getting? 10 nanosecond. That means it will take 10 nanosecond of time to reach this V naught from here to here. Is that clear to you? Now let's analyze what will happen at 0.5 nanosecond. Just analyzing what will happen at 0.5 nanosecond. At t equals to 0.5 nanosecond. So what is the frequency of this wave? 1 gigahertz. That means what will be this time period? Time period will be 1 nanosecond. Do you agree to this point? Time period will be 1 nanosecond. So at 0.5 nanosecond, this guy minus V naught would have come. That means here you would be having minus V naught at 0.5 nanosecond. At t equals to 0.5 nanosecond, here you would be having minus V naught. Are you able to understand why it is minus V naught? We started at t equals to 0. At t equals to 0, it was V naught. But just as the time goes, these values will start coming. V naught by under root 2, 0, then minus V naught by under root 2, then minus V naught. So at 0.5 nanosecond, you are having minus V naught here. Okay. So this point I am calling as AA dash. So A dash is at 0 only. Let's just say this is ground. So this is at 0 only, but point A is at minus V naught. Okay. Now where would have this V naught been? At t equals to 0, this V naught was here. Now in 0.5 nanosecond, how much distance this V naught would have covered? Distance traveled by V naught in 0.5 nanosecond. What will be the distance? Distance is equals to speed into time, right? So what is the speed? Speed is 3 into 10 to the power 8. And what is the time? Time is 0.5 nanosecond. Time is 0.5 nanosecond. Okay. So what you are getting? 0.5 meter. What you are getting? 0.15 meter. 0.15 meter. So let's just say this is complete length L. Complete length L is 3 meter. Then what would be 0.15? Basically 3 meter is equals to L. So 1 meter will be equals to L by 3. So 0.15 meter will be equals to 0.15 L divided by 3. So that would be 0.05 L. So at this distance, let's just say this distance BB dash is 0. This distance is 0.05 L. So in 0.5 nanosecond, this point would be at minus V naught and this point would have been at V naught at t equals to 0.5 nanosecond. What happened was these were two wires. First we applied some potential, then V naught came. Now this V naught started traveling. This V naught started traveling with the speed of 3 into 10 to the power 8. The total length is 3 meter. It will take 10 nanosecond of time to cover this complete length. Now we are analyzing at 0.5 nanosecond. So at 0.5 nanosecond, we got to know that this point would have been at minus V naught and this V naught would have traveled ahead. So this V naught would have reached at 0.05 L distance. Now what you are having? In the wire, you are having a potential difference. Since this is a wire, so it will have some resistance for sure. At 0.5 nanosecond, here you are having minus V naught potential and here you are having potential V naught. That means current would flow. Right? Here what was the scene? What was happening here? The complete 3 volt was coming. Like there was no potential difference between the wires. There was no potential difference between the wires. Complete 3 volt was coming here directly at VA, VB, VC. But here what is happening? Just as you close the switch, if the length of the wire is decent enough, then it is taking 10 nanosecond of time. But the input that you have applied, it has a time period of 1 nanosecond only. That means in 0.5 nanosecond, here you are having minus V naught and here you are having V naught. That is developing a potential difference, and because of that there is current flow. Even if this load was not there, even if these lines were open circuited, still the current would flow because there is potential difference. Now where that current would go? What I am saying is that if the circuit was something like this, still there would be some current. But where the current would go, that we will see. Do not worry about that. But the point you got to know that what we are going to study in this chapter. So these two wires that we have taken, these are known as transmission line. Two conducting wires separated by a media. two conducting wires separated by a media. In this case, this is air. Okay, it could be any dielectric, but in our case, since I am taking the speed equals to 3 into 10 to the power 8, that means this is air. Are you getting this point? So I'm not gonna write down all these points because no one will ask you, but you should have an idea of that, like what you are studying in this chapter. That idea you should have. Otherwise, there is no use of studying this chapter, right? So I hope you must have understood that we clicked then 0.5 nanosecond. This is minus V naught. This is plus V naught. This is our waveform. This is okay. This is also fine. This is also fine. Yeah, nothing else we need to erase, right? Okay. Now, when can I ignore this effect of this transit time? When can I ignore the effect of this transit time? What do you think? When this transit time is very, very lesser than this time period. If this transit time is very, very lesser than this time period, that means it will take, let's just say this is 10 nanosecond and this is some 1000 nanosecond. That means transit time is 10 nanosecond only, but this time is some 1000 nanosecond. That means it will take only 10 nanosecond of time just as you close the switch. Just as you close the switch, in 10 nanosecond, here V naught will reach. And in 10 nanosecond, since this is 1000 nanosecond, now I am assuming this is 1000 nanosecond. So in 10 nanosecond, V naught would have changed by a very minute amount. Basically, what I am saying is that just as I close the switch, it will take 10 nanosecond of time for V naught to reach here. Now, what will be the potential after 10 nanosecond? What will be the potential after 10 nanosecond at the source end? That will be somewhat lesser than V naught. That means potential difference will be very less. And if potential difference is very less, that means the current would be very less. Are you getting this point? What did I say? If my transient time is very low, that means you are taking very less time for the potential to reach here from here to here. Time taken for the potential to reach from here to here is very less. Here, what did we say? How much time you took for the potential to reach from here to here? 0 second only, no? Just as you close the switch, 3 volt reached here, 3 volt reached here, 3 volt reached here. So if this transit time is very low, lower than this time period, then you would feel like that it has reached V naught very quickly. This V naught would have reached here very quickly. And here also there would be some change, but the change will be very minute. Approximately the potential here and here both will be approximately equals to V naught only. So on the complete line, the potential will be approximately equals to V naught. So there will be no potential difference, there will be no current flow. Is that clear to you? No current flow between the wires. Certainly there will be current flow because here there is V naught, here there is ZL, so current flow will be V naught by ZL. So certainly current flow will be there, but if I am not connecting any load, if a load is not there, then certainly there will be no current flow. Are you getting this point? If load is infinity, and if I say here also there is V naught potential, here also there is V naught potential at the same time, both ends, all the ends are having V naught potential and there is no load, then there will be no current for sure. Is that clear to you? If I ask you, this is a resistor and this is 3 volt. What is the current in this resistance R? What you will say? Sir, 0 current, because there is no load. Basically here also there is 3 volt, here also there is 3 volt. So where would the current flow? The current cannot flow, right? So same thing is happening here. But that will happen only if your transient time is very, very less than time period. Is that clear to you? So let's remove it off. Okay, fine. So when can transient time effect can be ignored when transient time is very, very less than the time period. So TR is very, very less than the time period. Okay, what is your TR? Length divided by the speed. Length divided by speed, which is very, very less than. Can I write down 1 by F? Time period is 1 by F only, right? So what will be your length? Vp by F. And what is Vp by F? Lambda. Okay, if you like you might have studied this equation in your 11th 12th class, but even if you haven't studied, then you need to remember from now. Lambda is equals to Vp by F, and in some problems we used it in EM wave as well, as far as I remember. Lambda is equals to Vp by F, where F is the frequency, Vp is the speed. Okay, from now onwards you will be remembering it. So your length should be very, very less than your wavelength of the applied signal. So if this length is small, if this length L is small, smaller than what? Wavelength of this signal. This is your wavelength, no? If this was x coordinate, then this would have been your wavelength lambda. So if this length is very lesser than lambda, if this length L is very lesser than lambda, then it is fine. Then you can ignore the transient time effect. Otherwise, you cannot ignore it. Is that clear to you? Okay. So very important result. They will not ask question from this discussion, but this discussion was important. We spent 15 minutes here just for the fact that you should know what you are going to study in this particular chapter. Is that clear to you? Okay. So let's revise it again. That in network analysis, what we have studied, just as we close the switch, potential will be coming towards all the points, 3 volt, 3 volt, 3 volt. But here what is happening is that the length is finite. It is taking a finite time for the signal to travel. So if it is taking 10 nanoseconds of time, then we got to know that it will take from point A to from here to here, it will take 10 nanoseconds of time. Then what did I do? I analyzed it at 0.5 nanoseconds. So at 0.5 nanoseconds, I got to know that at this A dash point, you are having minus V naught. But at BB dash, that means at 0.05 L distance, this V naught would have traveled 0.05 L distance. That means at BB dash, you are having potential V naught. Since there is potential difference, there will be current flow. Where will the current go? That we will see. Do not worry about that. Okay. So yeah, at 0.5 distance, we got to know that this is the distance 0.15 m, that can be written as 0.05 L. This distance can be written as 0.05 L, which is at point BB dash. This is at point BB dash. Okay. So the potential has become here V naught. Because of the potential difference, there will be some current. So what you got to know that with respect to time, there is potential difference on the wire. But here in this case, with respect to time, there was no potential difference on the wire. This was also having 3 volt, this was also having 3 volt, this was also having 3 volt. Is that clear to you? Okay. And when this transient time effect can be ignored, if your length is very lesser than the wavelength of the applied signal. Okay. What this lambda is? Wavelength of the applied, wavelength of source signal, I will write. Wavelength of source signal. So this particular structure that we studied, this is known as a transmission line. Okay. So this was your transmission line. So we will study about it, but before that, let's see a basic mathematics. So even if you don't know, then you need to remember. If you know, then it is good. So e to the power theta plus e to the power minus theta by 2, that is known as cos hyperbolic theta. Okay. Cos hyperbolic theta. Even in engineering mathematics, we also don't study it. Right. In engineering mathematics, we also don't study hyperbolic function, but here sometimes it will be used. It will not be asked in the examination, but somewhere it will be used. So there you should not be getting confused that, sir, how did you write it? So e to the power theta plus e to the power minus theta divided by 2 is cos hyperbolic theta, and e to the power theta minus e to the power minus theta divided by 2 is sin hyperbolic theta. Okay. Just remember it. What do you mean by hyperbolic function? That time I am not gonna waste, otherwise it will take more 2 hours. And that will not be useful even in engineering mathematics. If it was useful in engineering mathematics, then certainly I would have spent some time. But no use there. Okay. Have we studied this function? E to the power j theta plus e to the power minus j theta by 2. Yes, we have studied. What was the answer? Cos theta, right? But if I solve by hyperbolic function, then what I would do? Cos hyperbolic j theta, right? Because what did I say? E to the power something plus e to the power minus something divided by 2 is equals to cos hyperbolic something. So here what is something? Something is j theta. So cos hyperbolic j theta. And this answer I already know is equals to cos theta only. So cos hyperbolic jx, if written, what will be your answer? Cos x. This will be highly used. Okay. This will be highly used. What about this? Do you remember this answer? Yes, I remember this answer. But as per this equation, what will be the answer? As per this equation, answer will be sin hyperbolic j theta. But do you remember the answer of this one? E to the power j theta minus e to the power minus j theta divided by 2. 2 or 2j? 2j is equals to sin theta. So what this will be equals to? J sin theta. So from this discussion, what you need to remember? This thing you need to remember. This thing you need to remember. Secondly, you need to remember this thing. These two things. Cos hyperbolic, if in the angle J is written, then J will be cancelled. J and H will be cancelled by each other. Simple answer you will get cos x. Here also both will be cancelled, but ahead you will add J. That's it. Sin hyperbolic Jx is equals to J sin x. That's it. What do you think? What will be your tan hyperbolic Jx? Tan hyperbolic Jx. So tan hyperbolic Jx would be, sorry, sin hyperbolic Jx divided by cos hyperbolic Jx. What is the value of sine hyperbolic Jx? That is J sin x. And what is the value of cos hyperbolic Jx? That is cos x. So what you are getting? J tan x. So from here, what did you see? That tan hyperbolic Jx is equals to J tan x. Another result which you need to keep in mind. So in sine also J would come out, in tan also J would come out, but in cos nothing would come out. Is that clear to you? Write down the formula of cot hyperbolic Jx. So you will do it on your own. The answer will be this. Okay, very easy. Minus J would come out. Because why is that so? Because it will be cos divided by sine. So cos will not take out anything, but sine will take out J. And if J goes upward, that would be minus J. So this also you must have understood. So very simple thing, you can keep only these two in mind. If you keep only these two in mind, these you can write down on your own only. Okay. And e to the power theta plus e to the power minus theta divided by 2 is equals to cos hyperbolic theta. This is just the proof of this. Okay. Some people do not even know that how this came. So this is just the proof that this you already know. So cos hyperbolic j theta is equals to cos theta only, and cos hyperbolic j sin hyperbolic j theta is equals to j sin theta. Is that clear to you? So this is just basic mathematics which you need to remember. Okay. Now let's see some basic concept. How do you make an inductor? This is an inductor, right? This is an inductor. Now when an inductor comes into action, let's just say this is a wire. This is a wire. Now your concept of electrostats will be used, that we studied in basics. So in a wire, if I current is flowing, then what happens? Magnetic field will be generated. If I current is flowing, then magnetic field will be generated. If magnetic field is there, that means magnetic flux is there. If magnetic field is there, then that means magnetic flux is there. Have you studied this relation phi equals to Li? In basic network analysis, you must have studied it. If magnetic flux is there, that means certainly there will be inductance. So if in a conductor current is flowing, then certainly there will be inductor. So this is an ideal inductor. But practically, if in a conductor current is flowing, then certainly there will be resistance as well. So practically, single inductor will never be there. Along with the inductor, there will be some resistance in the series. Is that clear to you? In a conductor, if current is flowing, so certainly there will be some resistance. There is some resistance. Along with that, if current is flowing, that means there is magnetic field. If there is magnetic field, that means there is magnetic flux. If there is magnetic flux, that means there is inductor as well. So if in a conductor current is flowing, that means there will be resistance as well, and there will be inductance as well. Is that clear to you? All these concepts will be used. Okay, later on it will be used. How do you make a capacitor? This is how you make a capacitor. When can a capacitor come into action? So what I'm going to do is that so let's just say these are two wires. Okay, these are two wires. Now on here the wires are excited by a source. These wires are excited by a source. Okay, so if they are excited by a source, that means here there will be some positive charge. Let's just say this is some positive charge is there and this is negative charge is there. So this will be zero charge, you can say, or some negative charge will be say there. Basically two wires are there, and in between I am connecting a battery. So some positive charge will go there and some negative charge will be there. Or you can say on this particular wire there will be positive charge, on this particular wire there will be zero charge. Or you can say here there is positive, here there is negative, right? And between two wires there is some dielectric, or you can say there is some air. Between two wires there is some air, or there is some dielectric. It could be any medium, it could be water as well, it could be air, it could be any other dielectric of any epsilon value. Okay, so two plates, one is having positive, another one is having negative. In between there is some dielectric, that means that will give rise to the capacitance. So between two conductors there will be one cap, and practically the cap will never come alone, it will come with the conductance. It will certainly come with the conductance. Okay, just like inductor comes with the resistance in series, capacitor comes with the conductance in parallel, or you can say resistance only, because what is conductance? Conductance is 1 by R only. This has a unit of mho. Okay, what is this? This is conductance, right? This is not resistance. I hope you know what is G. G is 1 by R, inverse of resistance. This can have a value of 2 mho. That means our resistance was 1 by 2 ohm. Okay, so in parallel of capacitance, I am showing a conductance, that is G. So that conductance is coming into action because of this dielectric only. Because of this dielectric, there is some capacitance and there is some conductance. So from this slide, what is the conclusion that you need to remember? If in a wire a current is flowing, then because of the conductor, because of the current, there will be some resistance, and because of the current, there will be magnetic field. If there is magnetic field, that means there is magnetic flux, and if there is magnetic flux, that means there will be inductance. So resistance and inductance will be there. Now, if there are two wires, that means current is flowing on both of the wires, or you can say here there will be positive charge, here there will be negative charge, and positive negative charge in between there is dielectric, then certainly there will be some capacitance as well. And if there is some capacitance, because of this dielectric, some conductance will also come into action. That is G. Okay, so here I am not going to write G equals to 1 by R. So can you tell me one thing, this R and this G, all these are like, what I mean to say is that G is equals to 1 by R. This I am writing. But this R and this G, both are same thing. No, certainly both are not same thing. Why is that so? This R is coming into action because of the current flowing into the conductor. This R is coming into the action because of the current flowing through the conductor. But this G is coming into the action because of the dielectric between two conductors. A very, very important point, like people will study complete transmission line, they will score full marks, but they do not know why this G came into action and why this R came into action. This R came into action because there was current flowing in this conductor. But this G came into action because there was dielectric between two conductors. Is that clear to you or not? So what do you think what this is associated with? This is associated with the conduction current, and this is associated with the displacement current. Two conductors, two plates, okay, in between there is some dielectric. Because of the changing electric field, there is some current that is known as displacement current. If you have studied previous chapter, there I discussed it, like I took 45 to 50 minutes just to discuss the displacement current. So this G is coming into action because of the displacement current, because there are two conductors, one is positively charged, one is negatively charged, in between there is some dielectric. So if there is changing electric field, certainly it will drive some conduction current. So that is the conduction current, sorry, not conduction current, it will drive some displacement current, and because of that displacement current, this G is coming into action. A very deep discussion, but I hope you are understanding what I am saying if you have studied displacement current, otherwise you will not be able to understand it. So this G is coming into action because of displacement current, and this R is coming into action because of conduction current. Is that clear to you? So both are complete different thing. Again, let me repeat it. In a wire, current was flowing. Because of this conduction current, this R came into action. Between two wires, there was some dielectric present, and there was positive charge here and negative charge here, and because of the changing electric field, there was a displacement current into action, and because of that displacement current, this G came into action. So what I am going to write here, this is the region of conduction current. So sigma C I am writing, or you will not be able to understand. Here I am writing conduction current. This is coming because of the conduction current, and this is coming because of the displacement current. So if someone is saying that there is no displacement current between the wires, between these two wires, if there is no displacement current, if someone is saying that there is no displacement current, then this G will not be there. So this question was asked in GATE examination in 2023, I guess, as far as I remember. In 2023 only this question was asked, that they asked you to draw the equivalent circuit of a transmission line, but there they said that in between the conductors, the medium which you are using, that is having Low's tangent equals to 0. What they are saying, this medium whatever that you are using, for this medium Low's tangent is 0. What do you mean by Low's tangent? Sigma upon omega epsilon. And if they are saying that medium is having sigma equals to 0, low standard is 0, that means sigma is equals to 0. If the medium is having no conductivity, that means there is no conduction current, there is no displacement current, there is nothing. So G will not come into action. So we will solve that problem, but here only I have given the solution. So there this G will not come into action. Is that clear to you? And you must have understood that why we are studying all these things in a very deeper manner. Two wires, current flowing, then RL. Two wires, in between there is dielectric, so G would be there. If G is there because of the dielectric, two wires, in between there is dielectric, so C will be there. And if C is there, that means G will also be there. Is that clear to you? So we will see a question as well that has been asked in GATE examination. In one of the assignment we will see, but here only you must have got the point. So what is the point? That in two wires, if the current is flowing, then there will be resistance and there will be inductance. Okay, and now resistance and inductance is there because of that current. Now two wires are there, one is positively charged, one is negatively charged, in between there is some dielectric, so there will be capacitance, along with that there will be some conductance as well, capacitance and conductance. Is that clear to you? Okay, yeah, fine then. Unit, let's go to the next slide. So there will be two very important terms which will come into action when we study transmission line, that is lumped element and distributed element. So this we have already studied in network analysis, but let's revise it again. So if I say lumped elements are there, then what do we mean by that? That if I show you this circuit and I am saying that all the elements present into this circuit are lumped element. What I am saying, in this circuit all the elements are present which are lumped element. So now if I say and I tell you that go and take out resistance R, then what you will do? Just take this resistance R out. That's it. Lumped elements means if I say that go Himanshu, take this inductor out. So you can just see the inductor and take it out. But if the elements are distributed, that means complete resistance is distributed along the line. Complete inductance is distributed along the line. Now if I say and ask you go and take out 4 ohm resistance. Go and take out 4 ohm resistance from this line. Can you take it out? No. Why is that so? Because there is no physical 4 ohm resistance is there. Here there is physical R ohm resistance. If I say and tell you that take out resistance R from this circuit, then you can see there is physical resistance R and you will take it out. But in this particular wire, if I ask you go and take out 4 ohm resistance, then you will say I cannot take it out. Because this 4 ohm resistance is distributed along the wire. So here what they are saying, resistance per unit length is 2 ohm per meter. That means in the complete wire there is 20 ohm resistance. So this 20 ohm resistance is distributed along the wire. So if I ask you take out 4 ohm resistance from there, then you would say that sir I cannot take out 4 ohm resistance. Say yes or no. If I ask you take out 6 Henry inductance, then you will say sir I cannot take out 6 Henry inductance because that is distributed along the complete network. But here they are individual elements. So that is the meaning of lumped and distributed element. Here we are not going to write down the definition that we have already written in network analysis course, right? But here I just wanted to give you the meaning of lumped and distributed element. I hope you must have understood. Let me take a break, then I will come back. Okay, you also take a break now. Yeah, so I hope you must have understood the meaning of this lumped and distributed element. Let's go to the next slide. So we are just studying basic mathematics now. We are not going into transmission line. Now once we go into transmission line, you will feel like that you have already studied everything. So till now you must have understood my teaching style, right? You have been following me for last 20-25 lectures. So there you would understand that first we study the basics, then we go into the topic, then topic becomes a cakewalk for us. So that's why we spend a lot of time on the basics, right? So the simple question is given, you need to find the value of current I. This potential V is there. Okay, this C is the capacitance, this G is the conductance. Okay, this G is conductance, not your resistance. So what will be the current? How will you write down the current? Current is simply V by the impedance provided by the capacitance. What is the impedance provided by the capacitance? That is 1 by j omega c plus V by impedance provided by the conductance. Impedance provided by the conductance, what that would be? 1 by g. Do you agree to this point? because here the resistance would have been 1 by G, no? So V by R is 1 by G, right? And what is the impedance provided by the capacitance? That is V upon, what is the impedance provided by the capacitance? That is 1 by J omega C. So V by the impedance, what is the impedance? 1 by J omega C, and that would be equals to your I. So V into J omega C plus V into G is equals to I. So from here, what did you get? G plus J omega C is equals to I. Okay. So this is the current I. Current I is V into G plus J omega C. Now you have studied EM wave, right? You need to write down the wave equations. But the point is, this is your positive y-axis. Your positive y-axis is in this direction. This is your positive y-axis. So can you let me know in which direction this wave is traveling? In which direction this wave is traveling? Positive y or negative y? Negative y. So what will be the equation? The equation will be V01 e to the power. I am assuming that the amplitude associated with this wave is V01. So V01 e to the power gamma y, plus gamma y or minus gamma y? Plus gamma y. Why is that so? Because it is traveling in negative y direction. This is traveling in negative y direction. Traveling in negative y direction. And this is traveling in positive y direction. So what will be the equation for this? That would be V02 e to the power minus gamma y. That would be V02 e to the power minus gamma y. So this is traveling in negative y, this is traveling in positive y. Is that clear to you? So these will be used when we study our transmission line. These concepts will be used. Okay. So let's see the equivalent circuit of transmission line. Can you draw it on your own? Certainly you can draw it on your own, because this is your transmission line. Two wires, two conducting wires separated by a dielectric. That is known as your transmission line. There could be different kind of transmission line that we will see in the end of the video. That is not important. Not in the end of the video, in the end of the chapter. That there could be different kind of transmission line. But this is highly used. That is known as two wire transmission line. Two conducting wires are there, in between there is dielectric, and these two wires are parallel. These two wires are parallel to each other, in between there is some dielectric. Here what you are going to apply? You are going to apply a source. Here at this end you are going to apply a source, and at the other end you will have some load. At the other end you will have some load. Okay. So that load I am not making. As of now you can consider that it is an open circuit load. So here there is a Vs source I am applying. Okay. So if there is a Vs source, that means there will be some current, and if there is some current, what does that mean? If there is some current, that means certainly there will be a resistance, and if there is current, that means there will be magnetic field. If there is magnetic field, that means there is magnetic flux. If there is magnetic flux, that means there is some inductance. So in the wire, if the current is flowing, so R and L will be there. So why this R and L came into action? Because of this current. Now there are two wires. This will be having some positive charge, and this you can say it is having zero charge, or you can say some negative charge. Two plates separated by some dielectric. That means it will have some capacitance, and if there is some capacitance, then certainly some conductance will also come into action. There you go. This is one of the equivalent circuit of your transmission line. But these elements will be distributed along the line. Are you getting this point? R, L, G, C. These are not separated elements. Like you cannot say that, sir, you take out R from here, L from here, G from here, C from here. No, they are distributed along the line. So what will be the unit of this R? The unit of this R would be ohm per meter. Unit of this L would be Henry per meter. Why is that so? Because it is distributed along the complete line. This complete transmission line is having resistance R, but that will have like 2 ohm per meter. In that manner it will be given, because it is distributed along the complete line. 2 ohm per meter, that means let's say this transmission line is of 2 centimeter. Then what will be the complete If this transmission line is of 2 centimeter, then what will be the complete resistance of this line? 2 into 2 centimeter into 10 to the power minus 2. So that would be 0.04 ohm. Okay. So ohm, Henry per meter. Then what will be the capacitance unit? That would be farad per meter. And what will be the conductance unit? That will be mho per meter. Okay, because they are distributed elements. Okay, distributed elements, not lumped elements. They are distributed along the complete line. So now you are able to understand why did we spend so much time on the basics. Now what I'm gonna do, I'm gonna take a small area, not area, sorry, a small portion of the line, delta y portion I'm gonna take. A small delta y portion I'm gonna take on this transmission line. So on this small delta y portion, what will be my resistance value? R into delta y. Because along the line there is R resistance. And if I write down R into delta y, that means in this small delta y portion, the total resistance is R into delta y. Because R is ohm per meter and delta y is meter only. So in this small portion, my total resistance is R into delta y. What will be my total inductance? L into delta y. What will be my total capacitance? C into delta y. And what will be my total conductance? That will be G into delta y. Is that clear to you? So same thing we are going to do. We are taking a small portion delta y. On the transmission line, we are taking a small portion, that is delta y. Okay. So how will I make this small portion? Now I am making this small portion only. I am making the equivalent of this small portion. Here I made the equivalent of the complete transmission line, R, L, G, C. But if I take small portion, delta y, delta y, delta y, here let's just call it delta y1 portion. Then I can take delta y2 portion. Like here I can take delta y2 portion. I can take delta y3 portion. अरे यार ये क्या हो गया? Wait a minute. Yeah, so what I was saying that I can take small portion on the transmission line, delta y1, delta y2, delta y3. But for now I am taking only this small portion delta y, and with regard to this small portion I am making my equivalent circuit. So only this portion I am making now. Only this much of portion I am making here now. So what that would be? RLGC. RLGC. So it will have R. Now in this small portion it will have resistance equals to R into delta y. Why is that so? Because R is your ohm per meter. In delta y, how much resistance will be there? R into delta y. In delta y, how much inductance will be there? L into delta y. In delta y, how much conductance will be there? G into delta y. And how much capacitance will be there? C into delta y. Capacitance will be C into delta y, and how much conductance will be there? G into delta y. Right? So this is small portion I am making. Only this portion I have made. So like this small portion, there would be a lot of portion on the transmission line. So basically this transmission line will be R, L, G, C. Then again R, L, let's make it more clear, R, L, G, C. Then again R, L, G, C. Then again R, L, G, C. So a lot of R, L, G, C will be there for delta y1, delta y2, delta y3, delta y3, delta y4, delta y5. In that manner, a lot of R, L, G, C will be there. So these R, L, G, C are known as primary constants. Okay. These are known as primary constants. Now we will derive transmission line equation. We will see with the intuition as well. We will see with the derivation as well that what kind of equation we will get. So mathematics we will also see, intuition also we will see. First let's see the intuition. Okay. So this is my transmission line. I am calling this end as y equals to 0 and this end as y equals to L. The complete length of the transmission line is L. So this end I am calling as y equals to 0 and this end I am calling as y equals to L. That means this is my positive y axis. Do you agree to this point? This is my positive y axis, right? That it is going in this manner. And some small portion I can take. So these will be the equivalent circuits, RLGC, RLGC. This is my source end. This is, I am not making the complete transmission line. Only some of the portion I am making. I just took this small portion and I made this circuit. Then I took this small portion, then I made this circuit. Okay. If I am calling this as delta y, then I should have called this as delta y dash. Because here I am taking delta y portion, here I would have taken delta y dash portion. Okay. And this is your source and this is your load end. So just as I close the switch, what will happen? Some potential will come here. So let's just say, just as you close the switch, some potential came here. Some potential Vx, I can say, some potential Vx came here. Okay. Now this capacitor was uncharged. So here there will be zero potential. So now what is happening? This is your resistance and this is your inductor. This is having some V potential, this is having zero potential. What it will become? It will become a RL circuit. And what RL circuit will do? RL circuit will drive some current, right? Initially it will have zero current, slowly it will build up the current. So here there is V potential, here there is zero potential. So now the current will be developed here. Now if this current is developed, what will happen? This current will charge this capacitor. Initially the capacitor was having zero voltage, now the capacitor will charge. So capacitor is charging. So here the voltage will build up. On this node, capacitor is charging, so here voltage is building up. So what will be the voltage? Some voltage is building up. Let's just say this voltage is V1 dash. Now this is having V1 dash potential and here there is zero potential. V dash potential and here there is zero potential. So this is V dash, this is zero. Again it will drive some current. So here also in this RL circuit some current is building up. Now because of this current, this capacitor will charge. So this capacitor will develop some voltage here. This capacitor will develop some voltage here. Then again there will be RL circuit, again there is some current. So what do you see? The current wave is traveling forward. Started from here, just as you applied some source, this current was developed and this current wave is traveling forward. Same thing is happening with voltage wave as well. Because of this current, this capacitor is getting charged. This capacitor is getting charged, that means it is developing some voltage. Because of this voltage, some current is developed. Because of this current, some voltage is developed. Because of this voltage, some current is developed. Because of this current, some voltage will be developed. And this process is keep on going. So voltage wave is traveling forward and current wave is traveling forward. So isn't it same as EM wave only? In EM wave, what was happening? EM wave energy was traveling forward. Here, VI energy is traveling forward. So what do you think? What will be the equation? V naught plus e to the power gamma z, that we will derive. But I hope you must have understood the intuition behind it. That how the voltage waves are traveling forward, how the current wave are traveling forward. So that only we need to study. And since we have studied EM wave in a very in-depth manner, it will be a cakewalk for us. Right? So let's derive the equations now. Okay. So let's remove it off. This was just the intuition that I wanted to give, that what is happening in the circuit. If you want to make it on your notes, then you can make it. But forget about the intuition. Now let's see the equations. From equations as well, we will verify our intuition. Okay. So now there are two things. You can derive the equation from source end. This is your source end, right? This is your source end. And the other one is your load end. So when we study EM waves, okay, when we study transmission line, we will always derive the equation from load end. That's why I gave this as y equals to 0 and this as y equals to L. So we will always derive the equation from load end. What happens? Transmission line becomes very tough. Why is that so? Because in the textbook as well, you will find that they will derive all the equation from source end. And when it comes to remembering the formula, they will ask you to remember the formula from load end. So everything becomes very complex and people don't understand transmission line. This is what happens when people study transmission line. But what we are going to do? We are going to derive the equation from load end only. So I will never ever take any equation from here. I will derive all the equation from here only. So what we are doing? We are assuming this as y equals to 0. A very important point. And this as y equals to L. That means what is your y? Y is the distance from load. Y is the distance from load. Say yes or no? Because when you say y equals to 0, that means you are standing at load only. But when you say y equals to L, that means you have covered L distance from the load. So y is the distance from load. A very, very important point where everyone gets confused. But you need to take care. All the formulas will be derived with respect to y. And y is the distance from load. So all the formula we are going to derive from the load only. Okay. Now what I am assuming, let's just say at this end, I am having V potential. What I am having V potential. So let's use different color of pen. So at this end I am having V potential. So can I write down the potential here will be V plus V dash? Okay, fine. Now I am saying that here my current is I plus, sorry, V plus delta V, not V plus V dash. The potential here is V plus delta V. Here I am saying that my current is I plus delta I. So from that, delta I current is flowing in this branch. Delta I current is flowing in this branch, and rest of I current is flowing here. What I assumed, and this is V plus delta V is also verified because this potential will be higher. Basically, if this is a resistance, this is a 3 ohm resistance, and I am saying 1 ampere current is flowing, and I am saying this is 6 volt, then what will be this potential? So this will have a 3 volt here, so this potential will be 3 volt. So current is flowing in this direction, I current is flowing in this direction. That means this will be V plus delta V potential, this will be V potential. Is that clear to you? Here I plus delta I current is coming. So delta I is given to this guy and rest I current is given to this guy. Is that clear to you? All these things, all these notation are clear. Okay. Just we are deriving the equation now. Now what I can write down? V plus delta V minus V divided by R delta Y plus J omega L delta Y. Basically you need to apply Ohm's law here. What you need to do? You need to apply Ohm's law. If it is not clear, I will make here. Resistance R is there. Inductance L is there. This is your V plus delta V. And this is your V. This is your resistance R into delta Y. What will be this? This will be J omega L delta Y. Because now I am writing down the impedance provided by the inductor. I hope you know what is the impedance provided by the inductor? J omega L. What is the impedance provided by the inductor? That is J omega L. And what is the impedance provided by a cap? That is 1 by J omega C. Right? And this is the current I. So what I can write down? V plus delta V minus V is equals to I into R plus delta Y plus J omega L delta Y. So what you are going to get? Delta V is equals to I R plus J omega L into delta Y. Right? So delta V by delta Y is equals to I into R plus J omega L. And if delta Y is tending to 0, if delta Y tends to 0, then what will happen? Like if delta Y, this is a very small portion. Delta Y that we have taken, that is a very small portion. This portion that we have taken, delta Y, that is a very small portion. If that is tending to 0, so you can replace this delta V by delta Y as dV by dy. So dV by dy is equals to R plus J omega L into I. So this is equation number 1. I should not keep it in box. Equation number 1 you have got. Okay. Same thing you can do with this GC pair. This is your GC pair. So here delta Y dash it is happening, right? So here I should not call it Y dash. I will call it Y only. Delta Y only. Let's call this as Y double dash. What I have done here is that, look, RLGC will be there on the complete transmission line. R, L, G, C. Then again RL will be there. R, L, G, C. G, C. So this portion I am taking as delta Y. Okay. This portion I am taking as delta Y. This portion I am taking as delta Y. This is some other GC. This is some other RL. I am only taking this portion as delta Y. I hope you must have understood the point. So this is delta Y because I want the equation in terms of delta Y only. I do not want to introduce delta Y dash. Okay, so this is some other GC. It will have some RL as well. This is some other RL. It will have some other GC as well. But here I am taking only these guy in action. GCRL. Delta Y. So this is my delta Y portion. Okay. Yeah. So what I can do now? So I will make the equivalent circuit here. This is your ground only. This is your V plus delta V. And this is your delta I. This was your G into delta Y and this was your, basically what will be the total impedance it will provide, 1 by G delta Y, and what will be the total impedance this will provide, 1 by J omega C delta Y. And you need to write down the current delta I. Can you write down the current delta I? Have we seen something like that? Yes. My delta I will be equals to whatever the potential is there into G plus J omega C. So my delta I would be equals to whatever the potential is there, V plus delta V into G plus J omega C into delta Y will also come outward. Basically, there the impedance provided was, here the impedance provided was 1 by J omega C and 1 by G. Here the impedance is 1 by G delta Y and 1 by J omega C delta Y. That's it. That's the only difference. Okay, well and good. It is fine to you, right? Delta I need to write. So V by delta V divided by the total impedance, that is G plus J omega C delta Y. That's it. This is what I have written, nothing else. Okay, so you can apply these equations as well. In that manner also you can get the same answer. So that's the thing I have done here. That's why I spent a lot of time previously. Now what I need to do, if I do this thing, V into, now I will multiply V with this guy and then I will multiply delta V with this guy. So V into G plus J omega C delta Y plus G plus J omega C delta Y into delta V. So both are very small quantity, right? Delta Y into delta V. So that can go to 0. This can go to 0, right? So 0 into something, this will go to 0 only. So what you are getting from here? Delta I by delta Y is equals to G plus J omega C into V. Delta I by delta Y is equals to G plus J omega C into V. Are you getting this derivation? What I am doing? V plus delta V, then delta I equation can I write down? Yes, very easily I can write down delta I equation. V plus delta V and into total impedance, that is G plus J omega C into delta Y. Not impedance, this is, sorry, this is admittance. This is not impedance, this is what we call admittance. So total admittance is G plus J omega C delta Y. If you don't know what is admittance, then no need to worry. This thing we have already done. So the same thing I have written here, nothing else. Okay. The same thing I have written. Then delta I by delta V will be G plus J omega C into V. So from here, if my delta Y is tending to 0, if delta Y is tending to 0, then what will be my di by dy? That would be G plus J omega C V. This is equation 2. And what was your equation 1? dV by dy R plus J omega L into I, right? This was your equation number 1. From here also you can get to know one thing, that a voltage is developing space varying current and a current is developing a space varying voltage. Voltage, current, current, voltage, voltage, current, current, voltage, wave is traveling. Same thing was happening when we study Maxwell's equation. Time varying magnetic field was generating space and time varying electric field, and space and time varying electric field was generating space and time varying magnetic field, and that cycle was keep on going, and you are having your EM wave. Same thing is happening here. Ditto same expression you will get. What I can do now? I will pick this equation. What I am going to do? Differentiate this equation on both of the side. Differentiating on both of the side. इसको टेढ़ा लिखा जा रहा है यार. Why it is going in this direction even though it is straight only? Still differentiating on both of the direction, what you are going to get? R plus J omega L di by dy. And what is the value of di by dy? From here I can pick from equation 2. Very easy derivation, right? Nothing complex is there. Every single thing we know about this derivation. That would be R plus J omega L. What is di by dy? Di by dy is G plus J omega C into V. So why did I do this step? Because I wanted the complete equation in terms of V. Now this is my second order differential equation which I can solve very easily. What I am going to do? I am going to keep this value as gamma square. Gamma square. So my gamma is under root. What is my gamma? My gamma is under root r plus j omega L into g plus j omega c. This is my gamma. What is the equation I am getting? Let me add a page. D square v divided by d square y is equals to gamma square v. Okay. So do you know the solution of this equation? Yes. In the solution of this equation, what do we get? V will be equals to C1 e to the power minus gamma y plus C2 e to the power gamma y. Say yes or no. This is what you get as the solution. When we were studying EM wave, what did we do? We told that there will be three solutions. There will be three solutions. C1 e to the power minus gamma z, C2 e to the power plus gamma z, and C1 e to the power gamma z plus C2 e to the power minus gamma z. I told you there will be three solutions, minus gamma z plus gamma z, and other one will be the linear combination of both of them. And then I told you that I will assume that my wave is traveling in positive z direction, and we will pick this equation and study about it. But here what we are gonna do, we are gonna take both of the waves, one which is traveling in positive y, other one which is traveling in negative y. So let me make the transmission line again, and then we will see what we are going to do. So this was my transmission line. Okay, here we got to know that this is your positive y direction, right? This is your positive y direction. This is your y equals to 0, this is your y equals to L, and positive y direction is this. So there are two waves, one is traveling in negative y direction and other one is traveling in positive y direction. Which one is traveling in positive y direction? This one is traveling in positive y direction, right? This is traveling in positive y and this is traveling in negative y. So C1 is associated with which one? C1 is associated with this or this. Which one is C1? C1 is this guy because it is traveling in positive y direction, and this is your C2. Now what is this? This is your source end. In case of transmission line, I am saying this is your source end and this is your load end. So from source this guy is going, right? From source this wave is going forward and this wave is coming back. From source, what source will do? It will develop some voltage, then some current, then voltage, current, voltage, current. So this wave is going forward. From source this wave is going forward, and after that here what is there? Here there is load. So from load this wave is coming back. So what do you think? Can I call this as incident wave? Can I call this is your load end which I am writing here? Can I call this as incident wave? And can I call this as a reflected wave? Look, a very important discussion we are doing, which a lot of students get confused. So this is my incident wave, this is my reflected wave. Can I call it in this manner? Because from the source voltage wave will go and it will come back. So the magnitude associated with the incident wave, I will call that V0 plus. The magnitude associated with the incident wave, I will call it V0 plus. So this C2 I will call as V0 plus, and the magnitude associated with the reflected wave, I will call that V0 minus. Is that clear to you? Okay, we did the complete derivation, we got the V expression in terms of y. So I am gonna write it down, Vy. This is my Vy. My Vy is C1 e to the power minus gamma y plus C2 e to the power gamma y. So I cannot keep C1, C2. I need to write down the value of C1, C2, that then only I can get the complete expression. So what I am saying, one wave is traveling in negative y direction, one wave is traveling in positive y direction. The wave which is traveling in negative y direction, the wave which is traveling in negative y direction, this is traveling in negative y direction. Why is that so? Because it is coming from the source. It is coming from the source end. So this is traveling in negative y direction and this is traveling in positive y direction. The wave which is traveling in negative y direction has an amplitude of V0 plus, because this I am calling as incident wave, because this is coming from the source. And the wave which is traveling in positive y direction, that means that is coming from the load. That means that would have been your reflected wave. So this I am calling as reflected wave. Incident wave, reflected wave. Okay. reflected wave is traveling in positive y direction and incident wave is traveling in negative y direction. So from here, what Vy equation I am getting? Vy equation you are getting as V naught plus e to the power gamma y. C2 is your V naught plus. C2 is your V naught plus. A very important discussion. Plus V naught minus e to the power minus gamma y. So this is the equation you are getting. Now your target would be to find the value of V naught plus and V naught minus. From here, what you can tell, this is your incident wave, and this is your reflected wave. So if I make the complete transmission line from source, what will happen? V naught plus wave will go there and V naught minus wave will come back. V naught plus wave will go there, V naught minus wave will come back. If you need to write down the equation of this wave, how will you write down? The amplitude associated is V naught plus. The amplitude associated is V naught plus. In which direction it is going? Since this is your positive y direction, then which direction it would be? Negative y. So V naught plus e to the power gamma y plus V naught minus e to the power minus gamma y. Till now in this whole derivation, this is the only conclusion which you need to remember. Is that clear to you? If there is some source, there will be some wave going here, some wave will be coming back. Two waves will be there. This I am calling as incident wave. This is my incident wave. And this is my reflected wave. See the direction of incident wave. The amplitude associated with the incident wave is V naught plus. Why is that so? Because this is coming from the source. That's why I am calling it V naught plus. Like there is no practical meaning that why you are putting plus. Just I am putting plus because it is coming from the source. That's why I am putting plus, nothing else. Okay. So V naught plus is the incident wave. Amplitude associated with the incident wave is V naught plus. And that is traveling in negative y direction. So V naught plus e to the power gamma y plus V naught minus e to the power minus gamma y. What is y here? Y is the distance from load. Okay. Y is the distance from load. A very, very important equation, a very, very important point. And this is the conclusion which you need to keep in mind. Very, very important. This is the point from where all the confusion starts. But we are not going into any confusion. We are just practically seeing what is happening. V naught plus, V naught minus, this is traveling in negative y, this is traveling in positive y. You can write down the equation, that's it. And what is y? Y is the distance from load. Distance from load end, not from the source end. Again and again I am repeating, distance from load. Now I need to write down I equation as well. So what I am going to do? Just differentiate this Vy equation with respect to y, because this was our equation 2, right? This was our equation 2, if you remember. This was our equation 2. dv by dy is equals to, this was our equation 1, sorry. dv by dy is equals to r plus j omega l into I. So this was our equation 1. So I will just differentiate it. What you will get once you differentiate it? So V naught plus e to the power gamma y, gamma. Basically you need to differentiate with respect to y. So V naught plus as it is, e to the power gamma y as it is, then differentiation of this guy, that will be gamma. Then differentiate with respect to y. So minus gamma will come here. Minus gamma V naught plus e to the power minus gamma y. Then this r plus j omega l can come downward, divided by r plus j omega l divided by r plus j omega l divided by r plus j omega l is equals to I. Since this will be a equation of, since this will be in terms of y only, so I am writing Iy. Is that clear to you? I just did the differentiation, nothing else. When I did the differentiation of this, gamma would come divided by r plus j omega l. When I did the differentiation of this, minus gamma would come divided by r plus j omega l. This is your Iy equation. Okay. So this is Iy equation we are getting. Now what I am defining? I am defining a term. What is that? I am defining a term. That term is r plus j omega l divided by gamma. This I am defining as to z naught, and I will call it characteristics impedance. What I am calling it? Characteristics impedance. Okay. We will discuss about it in a good manner. Just wait a minute. Okay. Just once we derive the equation, then we will discuss about this z naught as well. So do not worry about it. As of now, what I am defining a term r plus j omega l divided by this gamma, that is equals to z naught. This is what I am defining. This gamma can come downward, no? This gamma can come downward. So that I am defining as z naught. So what is the value of gamma? So Z naught would be equals to R plus j omega L. What is the value of gamma? Gamma is under root R plus j omega L into G plus j omega C. So what is the value of Z naught you are getting? Under root R plus j omega L divided by G plus j omega C. This is the value of Z naught you are getting. Certainly we will discuss about it, that what is the actual meaning of characteristic impedance, what is the actual meaning of input impedance. That is also a very important discussion. We will do that discussion, but as of now you just understand one thing, that I defined R plus j omega L divided by gamma is equals to Z naught. For now you just need to remember this thing, that's it. What you need to remember, that also I will tell. Just see the derivation, what you need to remember from that particular derivation, that certainly I am telling. As of now you need to only remember this thing, that my incident wave is V naught plus, reflected is V naught minus. Then can I write down the equation, incident and reflected, that's it. This is the only thing you need to remember. Now what we are getting, my Iy is equals to V naught plus divided by Z naught. Can I do this thing? Because gamma upon R plus j omega L is 1 by Z naught. So what I can do, V naught plus divided by Z naught e to the power gamma y minus V naught minus divided by Z naught e to the power minus gamma y. Okay, this is your Iy equation. Now what I am defining, Iy is equals to I naught plus e to the power gamma y plus I naught minus e to the power minus gamma y. So this is the other equation I am getting. No need to mug up these formula, but what you are understanding, that if there is forward wave of voltage, if there is forward traveling wave of voltage, then certainly there is forward current wave as well. Voltage wave is there, certainly there is current wave as well. In the same manner, if there is reflected voltage wave, then certainly there is reflected current wave as well. This I naught plus is equals to V naught plus by Z naught, and this I naught minus is equals to minus V naught divided by Z naught, minus V naught minus divided by Z naught. No need to remember it, but it will help us understanding Z naught value. What is Z naught? It will help us understanding that. For now, can you comment what is Z naught? What do you think what is Z naught? Z naught is the ratio of forward traveling voltage wave to the forward traveling current wave. That's it. Or you can say Z naught is the negative ratio of reflected voltage wave to the reflected current wave. So when I am defining Z naught, again I am saying, when I am defining Z naught, I am only considering incident wave and incident wave only. When I am defining the value of Z naught, then I am writing V naught plus divided by I naught plus. At that time I am considering there is no reflected wave. Actually what is happening in transmission line, there is incident wave, then there will be some reflected wave, then again there will be incident wave, then again there will be reflected wave. So there will be a lot of incident and reflected waves. But when I define the value of Z naught, that means only one incident wave. When I define Z naught, that means only one incident wave regarding the V naught I will take and one incident wave regarding the I naught I will take, and just simply calculate the ratio. That's it. Are you understanding this point? A very, very important point. Like people will be getting confused that, sir, what is input impedance of transmission line and what is Z naught? What is the difference between both of them? So about input impedance also we will discuss, but for now Z naught we are discussing. So when you define Z naught, at that time you only take forward traveling wave and forward current wave and just take the ratio. That's it. There is no reflection. This is what you consider. Is that clear to you? Okay. So this is the definition of characteristic impedance. In EM wave, there was intrinsic impedance. What was the value of intrinsic impedance? Neta, E by H. So you were taking forward E divided by forward H. Here what you are taking? Forward V divided by forward I. Here also you did not take any reflection into action. Here also you are not taking any reflection into action. So whenever you are defining characteristic impedance or intrinsic impedance, you are only taking into action forward way, or you can take backward into action as well. But when you are taking backward into action, when you are taking backward wave into action, so at that time you only need to consider backward wave only. Is that clear to you? Fine. Okay. So we will write it down. Certainly we will write it down, but we need to derive more expression as of now. So in this discussion, what all you need to remember? This thing you need to remember, that V naught plus will be going, V naught minus will be going, and if V naught plus and V naught minus is going, then certainly there will be associated I naught plus as well, I naught minus as well. That's it, nothing else. And will you be able to write down this equation? Yes. Y equals to 0, y equals to L. This is my positive y. That means incident wave is traveling in negative y. So V naught plus e to the power gamma y plus V naught minus e to the power minus gamma y. That's it. Okay. Yeah. So I will take a pause. Now we need to derive the value, not derive, we need to find the value of V naught plus and V naught minus. We need to find these values. V naught plus, V naught minus, and I naught plus, I naught minus. So these value we need to find. How we will find? Using the boundary condition, or you can say, basically I will put y equals to 0. At y equals to 0, what you are getting? At y equals to 0, what will be the value of Vy? That will be V naught plus V naught minus. And what will be the value of Iy? That will be I naught plus I naught minus. From there I will get the equations and I will find the values. Okay, so I will take a break. But before that, you just let me know one thing. This is my VL and this is my IL. Basically, this is my load voltage and this is my load current. So what will be the value of ZL? ZL will be VL by IL, right? Here there is source, right? From source there will be source current. So at the load as well, there will be load voltage and load current. So this is what I have defined, because these will be used. These will be used in our equation. So in the transmission line, from the source VSIS is going, at the load you are having VLIL, and this is your ZL. Okay, very simple thing I have defined, very simple thing. So now we will derive the value of V naught plus and V naught minus, but I will take a break. You also take a break, drink some water, because it is, weather is changing frequently, okay, and everyone is getting ill, right? Everyone is getting sick. So yeah, you also drink some water, then we will start. Yeah, so we are back. We need to find the value of V naught plus, V naught minus, I naught plus and I naught minus. So let's call this as equation 1 and this as equation 2. This equation I am calling as equation 2. Now at y equals to 0, what will be the value of my Vy? At y equals to 0, what I am saying, at y equals to 0, what will be the value of Vy? At y equals to 0, the voltage is equals to VL only, right? That would be equals to VL. And from equation 1, what do you get to know? If you put y equals to 0 here, what do you get? V naught plus V naught minus. So what you are getting? V naught plus V naught minus. So VL is equals to V naught plus V naught minus. This is what you are getting. From here, VL is equals to V naught plus V naught minus. This is what you are getting. This I am calling as equation 3. You can put y equals to 0 here as well. If you put y equals to 0 here, that means what will be the value of Iy? At y equals to 0, what is your current? At y equals to 0, what is your current? Current is equals to load current. So at y equals to 0, at y equals to 0, Iy is equals to IL only. And what is your IL equals to? IL is equals to, if you put y equals to 0 here, what do you get? V naught plus divided by Z naught minus V naught minus divided by Z naught. So from here, what you are getting? IL Z naught is equals to V naught plus minus V naught minus. So two equations you are having. What all equation you are having? VL is equals to V naught plus V naught minus, and IL Z naught is equals to V naught plus minus V naught minus. And if I add both of them, if I add both of these equations, this I called as equation 3, this was equation 4. I am just finding the value of V naught plus and V naught minus. So if I add both of them, what I am gonna get? 2 V naught is equals to VL plus IL Z naught. So V naught plus 2 V naught plus actually. V naught plus will be equals to, if I add both of them, this is what I am getting. This is my V naught plus. You don't need to mug it up. You don't need to remember it. Okay. But it will be used somewhere. That's why I am keeping it in the box. It will be used somewhere in our analysis. And what will be your V naught minus? So if you subtract both of them, then you will get V naught minus value. Just did nothing. I had the equations. In those equations, I just put the value at y equals to 0. Because at y equals to 0, I know that my voltage is VL and my current is IL. Is that clear to you? So this equation I can write down very easily. This equation I can write down very easily. And this equation also I can write down very easily. From there, I just got these expression. Now what I need to do? In the equation 1, I will put the value of V naught plus and V naught minus from equation 1. Okay, so this is the easiest way of this derivation. Otherwise, you would find the derivation in the textbook very complex. But this is the easiest way. We are doing just nothing. We can write down the wave equation. Then we just need to find out the values. That's it. So V naught plus and V naught plus is traveling in negative y direction, and V naught minus, this is traveling in positive y direction. Okay. So from here what I can do, VL I can take common. Along with VL you are having e to the power gamma y plus e to the power minus gamma y divided by 2 plus IL Z naught. Along with IL Z naught, along with IL Z naught you are having e to the power gamma y minus e to the power minus gamma y divided by 2. This is what you are having. What is the value of this guy? What is the value of this guy? Value of this guy is VL cos hyperbolic gamma y plus IL Z naught sin hyperbolic gamma y. That's it. This is the Vy equation you are getting. Is that clear to you? Similarly, you can find the value of I naught plus and I naught minus. What will be the value of I naught plus? I naught plus will be simply this divided by Z naught. That will be your I naught plus. You can see here what is your I naught plus. I naught plus is V naught plus divided by Z naught. And what is your I naught minus? Minus V naught divided by Z naught. So what will be your I naught minus? I naught minus will be negative sign and divided by Z naught. And then you can put the values and you can get the expression. So similarly, Vy expression that we got, in the same manner, similarly you will get the expression of Iy as well. So what will be the expression of Iy? That would be equals to IL cos hyperbolic gamma y plus VL by Z naught sin hyperbolic gamma y. Okay. So this is the expression of Iy you will be getting. So this was your Iy, and what was your Vy? Vy was VL cos hyperbolic gamma y plus IL Z naught sin hyperbolic gamma y. Need to remember it. Okay. What you need to do, remember this expression you are going to remember. So till now what we have, till now what all points we need to remember, till now what all we have studied. Vy equation we studied. What was that? In Vy equation I am writing down the incident wave as well and reflected wave as well. So my incident wave V naught plus, that was traveling in negative y direction, plus V naught minus, that was traveling in positive y direction. Is that clear to you? If I write down my Iy equation, so with respect to the forward traveling wave, I will have a forward current wave as well and a returning current wave as well. Returning current wave as well. One thing I know, what do I know? That my I naught plus is equals to V naught plus divided by Z naught, and I naught minus is equals to minus V naught divided by Z naught. So from here I can define my Z naught. So Z naught is coming out to be V naught plus divided by I naught plus, or minus V naught minus divided by I naught minus, that is equals to under root R plus j omega L divided by G plus j omega C. This is one of the way of writing it. Then this V naught plus and V naught minus expression, that you don't need to remember. This expression you don't need to remember. But what is the final result you are getting? Vy. This you need to remember. What is that? VL cos hyperbolic gamma y. How will you remember it? So first you are writing the expression of V. So you will start your answer from VL. Basically we are writing all the things from the load end, right? All the things I am writing from load end. Now I am writing down the expression of V. So whether I will start from IL or VL, I will start from VL. So VL, because this is the expression of voltage. So VL cos hyperbolic gamma I. Now I will write down the current. So if I need to write down the current, so IL, but this is the expression of voltage. So IL into some impedance, that is Z naught. Then sin hyperbolic gamma I, gamma y. And if I need to write down Iy, so now I am writing current. So first I will write down current, IL cos hyperbolic gamma y. Now I will write down voltage. What is the voltage? VL. And if that I need to divide by some impedance. So divided by Z naught sin hyperbolic gamma y. So till now whatever the derivation we have seen, from the derivation you just need to remember these things. That's it. If you remember only this much summary, here what I am writing down, this is the summary. If you remember only this much summary, that is more than enough for you to solve any problem regarding this concept. So derivation, you must have understood how we proceed in the derivation, right? We got to know there is forward traveling wave, there is reflected wave as well. Incident wave is there, reflected wave is there. Incident wave is traveling in negative y direction, reflected wave is traveling in positive y direction. Based on that, we wrote down voltage and current equation. So what is this? Incident wave. And this is your reflected. And both combined is getting your Vy. Similarly, Iy. And from there we defined characteristic impedance, that is known as Z0, V0 plus divided by I0 plus. So till now in our discussion, you need to understand that transmission line is RLGC, okay, and then these equations. That's it. We have spent roughly around 70 to 80 minutes. In 70 to 80 minutes, this is the only summary. Okay, well and good. Now we understood this intrinsic impedance. So sorry, not intrinsic impedance, characteristic impedance, not intrinsic. Intrinsic impedance is term used in EM wave. So here we use the term characteristic impedance. So what is the meaning of characteristic impedance? So characteristic impedance is the ratio of the amplitude of a forward traveling voltage wave to the forward traveling current wave. So only one wave at a time you will take, not both combined. Okay. So V0 plus divided by I0 plus or V0 minus divided by I0 minus, but not both combined. Here I am not going to do Vy by Iy. Z0 is not equals to Vy by Iy. Because in Vy expression you are having forward traveling wave as well and returning wave as well. Both combined. All the waves combined you are having. But when we calculate Z0 value, only forward you need to take. Here also I am taking forward only. So that's the very important thing. What is this known as? This is known as input impedance. So that we are going to see in the next slide, but here we will see characteristic impedance. So once you are writing characteristic impedance, so this is forward traveling voltage wave and this is forward traveling current wave. So simply the ratio of that. So what I have written, the ratio of amplitude of voltage and current of a wave traveling in one direction along the line when there is no reflection in the other direction. That means only one direction wave we are taking. So my Z0 is defined as V0 plus divided by I0 plus, and when we were deriving the expression, what did we get to know? It was coming out to be R plus j omega L divided by G plus j omega C. You can relate it with the neta. What was your neta? J omega mu upon sigma plus j omega C. Sorry, sigma plus j omega epsilon. So say in the same manner you can relate it here. Okay, here R plus j omega L divided by G plus j omega C. Is that clear to you? A very important expression will be used. This is your characteristic impedance. Okay, this is your characteristic impedance. Now tell me one thing, from here, from this Vs, if some V0 plus wave is coming, from this Vs, if some V0 plus wave is coming, what impedance it will see? Z0, right? Because V0 plus will go here and it will see, okay, this is the transmission line, it is having Z0 impedance. Ahead also there is Z0 impedance, Z0. On the complete transmission line, it will see Z0 impedance because the ratio of V0 plus divided by I0 plus is equals to Z0 plus. Okay, so just as V0 plus gets out, it will always see Z0 impedance, right? Let's see a numerical, very easy numerical. At a point in transmission line, the forward voltage and forward current are 12 volt and 240 milliampere. Determine the characteristic impedance. So what will be the characteristic impedance? Only the forward voltage is given and only the forward current is given. So 12 volt divided by 240 milliampere, so that would be 0.24 ampere, right? 240 milliampere, 0.24 ampere. So if you solve it, 50 ohm you are getting. So that is the value of Z0. Okay, very easy numerical, just to build up the concept that what is the value of Z0. Now what is your input impedance? Okay, what I am saying, impedance of a transmission line looking towards the load. Basically you need to tell the impedance. What I am doing is that, let's just say at a very random point I am standing on transmission line. At a very random point I am standing, and now I ask you, what is the impedance do you see from here? What is the impedance do you see from here? At this point in transmission line, what is the impedance you see? So what you are going to do? You are going to do at this point what is my voltage divided by at this point what is my current. That would be the impedance at this point. I am not talking about input impedance. On transmission line at a random point, what will be my impedance? That I am telling. Input impedance we will certainly talk about. Basically from here if I see the impedance, that will be my input impedance. What will be your input impedance? On this particular graph only, if you draw input impedance, so what will be the input impedance? This will be your input impedance. If you cover the complete distance L, then this is known as your input impedance. That's it. There are two terms, impedance at a certain point and input impedance. Let me explain it in this manner. This is resistance R, this is resistance R, this is resistance R. R, R, R. If I ask you what is the impedance here, what you will say? 2R, R plus R. But if I ask you what is the impedance here, R plus R plus R, 3R. So at any random point, if I take a point here, A dash, and there if I am asking you the impedance, then what will be your answer? That's our Vy divided by Iy. That's it. So what is your Vy expression? Do you remember it? Yes, because I asked you to remember it. What is your Vy expression? VL cos hyperbolic gamma L plus IL Z naught sin hyperbolic, not gamma L, sorry, gamma Y, because we are writing in terms of Y, sin hyperbolic gamma Y. And what is your Iy? Iy is IL cos hyperbolic gamma Y plus VL by Z naught cos hyperbolic gamma Y plus VL by Z naught sin hyperbolic gamma Y. Now I need to calculate ratio of both of them, Vy by Iy. So what you will get? Just write down the ratio. So this is what you are going to get: VL cos hyperbolic gamma I plus IL Z naught sin hyperbolic gamma Y, and IL cos hyperbolic gamma I plus VL by Z naught sin hyperbolic gamma Y. Now you take this Z naught here, this Z naught here. So in the denominator there is Z naught, so IL Z naught, and then one Z naught will go upward. This Z naught will go upward. Simple mathematics it is. IL Z naught, then VL as it is, this Z naught will go upward, that this Z naught will come here. Now what I am going to do, in the numerator and denominator I am going to divide by IL. In the numerator and denominator I am going to divide by IL. So I am dividing by IL. So what will be the value of VL by IL? VL by IL, that would be equals to ZL, right? VL by IL. VL, here it was VL, and this is your IL. So VL by IL is equals to ZL. So ZL cos hyperbolic gamma Y plus Z naught sin hyperbolic gamma Y divided by Z naught cos hyperbolic gamma Y plus ZL sin hyperbolic gamma Y. Now in the numerator and denominator I am dividing by cos hyperbolic gamma Y. In numerator and denominator both I am dividing by cos hyperbolic gamma Y. So what I am going to get? Zy is equals to Z naught into ZL plus Z naught tan hyperbolic gamma Y divided by Z naught plus ZL tan hyperbolic gamma Y. That's it. This is your Zy. So at any point, at any random point in transmission line, if I am asking you the impedance looking towards the load, then what it would be? Z naught into ZL plus Z naught tan hyperbolic gamma Y divided by Z naught plus ZL tan hyperbolic gamma Y. This you need to remember. And what is Y here? Here Y is distance from load. A very important thing. Distance from load. So in the examination, what kind of questions will come? At lambda by 2 distance from load, at lambda by 2 distance from load, what is your impedance? They will not ask you input impedance, because if they ask you input impedance, everyone remembers tan hyperbolic gamma L. So everyone will be writing down L there. But they will ask you at some distance from load. They will not ask you input impedance. They will ask you at lambda by 2 distance from load, or at L by 2 distance from load, what is the impedance? So then you need to apply this formula. And if they ask you input impedance, then what you need to do? You just need to put Y equals to L. That's it. In this formula, if they are asking you input impedance, then simply Y equals to L you need to put, because at Zy equals to Zin, Y is equals to L. So simply Y equals to L you need to put. That's it. So Zin equals to Z naught into ZL plus Z naught tan hyperbolic gamma L divided by Z naught plus ZL tan hyperbolic gamma L. This will be your input impedance. That's it. Is that clear to you? We will discuss more about input impedance certainly, but as of now, this is the formula we are getting. Now in the input impedance and in the characteristic impedance, what is the difference? In characteristic impedance, you are only taking forward divided by forward, but here total divided by total. Vy divided by Iy. So in Vy, you are having forward as well and returning as well. Both combined is your Vy. So that is the difference. Are you getting this point? So from this Vs source, if V0 plus is getting out, from this Vs source, if V0 plus is getting out, just as the starting, just as I close the switch, what will happen? V0 plus will go out. So if V0 plus goes out, what it will see? It will see Z0 or it will see Z in. Think about it and tell me. Just as I close switch, some voltage wave will come out from this Vs, that is your V0 plus. So this V0 plus will see Z0 impedance or Z in impedance. It will see Z0 impedance. Why is that so? Because at that time there is no reflected wave. Just as you close the switch, V0 plus goes out, so only incident wave is there. And incident wave divided by incident voltage wave divided by incident current wave, what does it see? Z0. But if at the steady state I am talking about, at steady state means, at steady state there will be incident wave as well, reflected wave as well, then another incident wave, another reflected wave. So a lot of incident reflected wave will be there, and combined you will be getting Vy, combined you will be getting Iy. So at steady state you will see Z in, but just as the switch is closed, you will see Z0. A very important point which a lot of guys don't know. When we study transient on transmission line, I will tell you that initially you will replace the circuit with Z0. Everyone mugs it up that why do we replace it with Z0? What is the reason why do we replace it with Z0 initially? Because just as you close the switch, only one wave is there, that is forward traveling wave. The returning wave will come later on. Once it reaches there, it will be reflected back. Then the returning wave will come. Just as you close the switch, only V0 plus goes out. And V0 plus will see only Z0 impedance, not Z in impedance. Z in impedance is the impedance seen when there is incident wave as well and reflected wave as well. Both combined will see Z in. Is that clear to you? So at steady state, the transmission line can be replaced with Z in. But once the circuit start at t equals to 0 plus, the transmission line will be replaced with Z0. We will see it again and again, okay, do not worry, but later on it will come, that's why I just explained it here. When we study transient on transmission line, a very important point, a very important chapter, I should not a chapter, a very important topic, transient on transmission line. So there we will study it when you will replace the transmission line with Z in and when you will replace the transmission line with Z0. So very important thing, that's why I am focusing too much on Z in and Z0. Both are different things. So Z in is defined when the incident, reflected, everything is there, but Z0 is defined when only incident is there. Is that clear to you? Fine? Okay. So yeah, input impedance we have written. Now there is something called reflection coefficient. Okay, reflection coefficient, do you remember in our EM wave? What was the reflection coefficient? For normal incidents, what was the reflection coefficient? Neta 2 minus neta 1 divided by neta 2 plus neta 1. So there was the case of oblique incidence as well. Why is that so? Because E and H are vector quantity. But here V and I are scalar quantity. So there is no role of direction. That's why transmission line is easy. There E and H are vector quantity. So you need to take direction and all those things in action. But here they are scalar quantity. V0 and I0 are scalar quantity. So there is no role of the direction. That's why it is easier for us. Right? So similarly, we will write down the transmission coefficient. Sorry, reflection coefficient. Reflection coefficient here we will write down. So what is known as reflection coefficient? So in our voltage wave, in this equation, what we are having forward traveling wave and backward traveling wave. Basically, we are having incident wave as well and reflected wave as well. So what is your Vy? Complete Vy is V0 plus e to the power gamma y plus V0 minus e to the power minus gamma y. So what is known as reflection coefficient? Reflection coefficient is the ratio of reflected wave to the incident wave. That's it. So this is defined as reflection coefficient at any random point on transmission line. Basically, if I am saying that what is your reflection coefficient at this point here? What is my reflection coefficient here? Reflection coefficient, voltage reflection coefficient. Since we are dividing by voltage and voltage, so this is defined as voltage reflection coefficient. So we are talking about voltage reflection coefficient. So voltage reflection coefficient at any random point on transmission line, is defined as ratio of the reflected wave to the incident wave. So V0 plus e to the power minus gamma y divided by V0 minus e to the power minus gamma y divided by V0 plus e to the power gamma y. So what you will get? This is what you will get. And V0 minus divided by V0 plus is equals to e to the power minus 2 gamma y. Now what is the value of V naught minus and V naught plus? So did we derive anything like that? What is the value of V naught plus? V naught plus VL plus IL Z naught divided by 2, and what is the value of V naught minus VL minus IL Z naught divided by 2? So this I will write down again. V naught plus is VL plus and V naught minus is VL minus IL Z naught divided by 2. Okay, so I am just writing down the value of V naught minus divided by V naught plus. Then I will just put the value here. That's it. So what is the value you are getting? VL minus IL Z naught divided by VL plus IL Z naught. And if I divide by IL on both of the side, in numerator as well and in the denominator as well, what I am doing, I am dividing by IL. So what I will get? VL by IL is equals to ZL minus Z naught, and VL by IL is equals to ZL, and this will be plus Z naught only. So this is what you are getting, V naught minus divided by V naught plus, ZL minus Z naught divided by ZL plus Z naught. So this is your voltage reflection coefficient, that is ZL minus Z naught divided by ZL plus Z naught, but at any random point. So e to the power minus 2 gamma y is also there. Very, very important thing. Okay. Usually what people remember, this formula they remember. But this is the reflection coefficient at load. Why is that so? Because if I am calculating the reflection coefficient at load, that means I will put y equals to 0. And if I put y equals to 0, what I am getting? ZL minus Z naught upon ZL plus Z naught. But this is at the load. If I ask you at any random point, if I ask you at a distance lambda by 2 from the load, what will be my reflection coefficient? So which formula you will apply? ZL minus Z naught upon ZL plus Z naught. No, this complete formula you will apply. What I am saying, reflection coefficient at any random point from the load. Y is the distance from load. Again, I will write it down. What is Y? Y is the distance from load. So at any random point from load, if I ask you what is the value of your reflection coefficient, then what you will do, ZL minus Z naught upon ZL plus Z naught e to the power minus 2 gamma y. Okay. And if I ask you the reflection coefficient at load only, what that would be? Reflection coefficient at load, that means you just need to put y equals to 0. So if I put y equals to 0, what I will get? ZL minus Z naught upon ZL plus Z naught. But this we are talking about voltage reflection coefficient. Okay. We can comment about current reflection coefficient as well. So that we will see. But at the load, what will be your reflection coefficient? What will be your voltage reflection coefficient at load? So y equals to 0 you will put. So what you are getting? ZL minus Z naught upon ZL plus Z naught. Okay. And what this is equals to? What this is equals to? ZL minus Z naught upon ZL plus Z naught. ZL minus Z naught. ZL minus Z naught upon ZL plus Z naught is equals to V naught minus divided by V naught plus. Right. So what is actually happening? This is your transmission line. Here there is load. Here there is load. So what is happening? Some incident wave is there, which is having V naught plus. Now it will be reflected back. Now what will be the amplitude of this wave? Amplitude of this wave will be gamma voltage, but at load into V naught minus. Say yes or no? Because what is your, sorry, V naught plus, sorry. Because what is your V naught minus? V naught minus is equals to gamma voltage, that means voltage reflection coefficient at load into V naught plus. This is your V naught minus. So I know that my incident wave will have the amplitude of V naught plus and reflected wave will have the amplitude of V naught minus. But that is equals to gamma VL V naught plus. So simply what I can do, plus gamma VL V naught plus e to the power minus gamma Z. That's it. Okay. Now this gamma VL can be a complex quantity. Why is that so? Because ZL can be complex. Z naught can also be complex. Everything can be complex. So it can be a complex or real quantity depending on the value of ZL and Z naught. So here some angle may come up. And this kind of expression where you have seen in standing wave pattern, because there is incident wave, there is reflected wave, both combined will make a standing wave. So we need to study standing wave pattern as well. That we will study in the third or fourth video. Okay. So, but you are connecting the dots now, right? We are connecting the dots. There also we studied about the standing wave pattern for electric field and magnetic field. There we saw that there is forward traveling electric field. Because of the boundary in between, there was a reflected electric field as well. Both combined were making what they were making, standing wave pattern. So there we calculated the reflection coefficient. So reflection coefficient for electric field. What we calculated? Reflection coefficient for electric field. Neta 2 minus neta 1 divided by neta 2 plus neta 1. Since there was direction associated, so we need to remember the assumption as well. What was the assumption? That incident and reflected electric field both are having same direction. That was the assumption, right? We assumed that the magnetic field will change its direction, right? So that was the assumption, but that we studied in EM wave. So I am just correlating the things, okay? There what did we study? That your reflection, electric reflection coefficient is equals to the negative of magnetic reflection coefficient. This is what we studied. So here what you are going to study? That your voltage reflection coefficient is equals to the negative of current reflection coefficient. That's it. There your electric reflection coefficient was negative of the magnetic reflection coefficient. Here your voltage reflection coefficient will be equals to the negative of current reflection coefficient. That's it. Is that clear to you? Okay. So this is one of the expression that we need to keep in mind, that V0 minus can be written as gamma voltage reflection coefficient, but at load. Gamma voltage reflection coefficient at load V0 plus e to the power minus gamma z, where gamma VL is equals to ZL. What is gamma VL equals to? ZL minus Z0 upon ZL plus Z0. Gamma Vy is equals to V0 plus e to the power gamma y. Sorry, V0 minus e to the power minus gamma y divided by V0 plus e to the power gamma y. But if I calculate at load, then y equals to 0 I will put, that will be equals to V0 minus divided by V0 plus. Is that clear to you? I know the things are being like, there are a lot of things. It feels like that there are a lot of things, but when we write down the summary, you will realize that only a few things are there. Okay. Till now, this summary we have written here, the expression summary we have already written. Then we studied about Z0. Okay. Then we studied about input impedance, and then we are studying about reflection coefficient. Things will not get meshed up. We will again study about all these things. So one by one also we will study, but as of now we are just compiling the formula. Is that clear to you? So actual reflection coefficient on transmission line at any distance y from the load is this, ZL minus Z0 upon ZL plus Z0 e to the power minus 2 gamma y. But if they are asking certainly at the load only, so this will be the formula. That's it. Okay. Is that clear to you? And this value is equal to V0 minus divided by V0 plus. Is that clear? Okay. We will certainly write down all the summary. Now let's see current reflection coefficient. So what do you think? What will be your current reflection coefficient? So reflected current wave divided by incident current wave. This is your reflected current wave divided by incident current wave. So what you are getting? I0 minus divided by I0 plus e to the power minus 2 gamma y. What is the value of I0 minus? I0 minus is equals to minus V0 minus divided by Z0. What I am doing, I will do it here. What I am calculating? I0 minus divided by I0 plus. So what is your I0 minus? Minus V0 minus divided by Z0 divided by V0 plus divided by Z0. So what you are getting? Minus V0 minus divided by V0 plus. And what is the value of V0 minus divided by minus? V0 minus divided by V0 plus. What is the value of this? This is your minus of ZL minus Z0 upon ZL plus Z0. Basically same thing I am going to put here. What is your I0 minus divided by I0 plus? That is equals to minus of ZL minus Z0 upon ZL plus Z0 e to the power minus 2 gamma y, and that is equals to your gamma I. So this is equals to the negative of gamma v, right? Gamma I is negative of gamma v, right? Because this is your gamma v. So negative of gamma v. That's it. Okay. So gamma is the negative of gamma v. So we will always remember the formula of gamma v. We will always remember the formula of gamma v. We will never remember the formula of gamma I. We just need to take negative of that. That's it. Okay. And if you write down the gamma I expression at load, what that would be? Minus sign outward, then ZL minus Z0 upon ZL plus Z0. So that is the formula of gamma I, but at load. ZL minus Z0 upon ZL plus Z0, but a negative sign is there. Is that clear to you? Okay. So reflection coefficient, in reflection coefficient, what all you need to remember? that what is the formula of reflection coefficient? ZL minus Z0 upon ZL plus Z0 e to the power minus 2 gamma y. That is the formula. Okay, where y is the distance from load. That is the formula we need to remember. Then at the load y equals to 0, so ZL minus Z0 upon ZL plus Z0. And the voltage reflection coefficient is negative of current reflection coefficient. Only three things you need to keep in mind. And this also you can keep in mind, that ZL minus Z0 upon ZL plus Z0 is equals to V0 minus divided by V0 plus. So only these things you need to keep in mind. Is that clear to you? So let's write down all the summary, whatever that we have studied. Voltage expression on transmission line. What was that? Two expression we studied. V0 plus e to the power plus gamma y plus V0 minus e to the power minus gamma y. And that was equals to VL cos hyperbolic gamma y plus IL Z0 sin hyperbolic gamma y. What was the current expression? I0 plus e to the power gamma y plus I0 minus e to the power minus gamma y, and that was equals to IL cos hyperbolic gamma y plus VL by Z0 sin hyperbolic gamma y. Okay, did we write down the value of Z0? Here we can write down about Z0 as well. What is your Z0? Z0 is equals to V0 plus divided by I0 plus is equals to minus V0 minus divided by I0 minus. What is the impedance at any point? That is equals to, starting from Z0, then alternatively I need to write ZL and Z0. So what I will write? Z0 into ZL plus Z0 tan hyperbolic gamma impedance at any point. So gamma y I will write down divided by Z0 upon ZL tan hyperbolic gamma y. This is my ZY. Right? If I need to write down the input impedance, that I will at y I will just put L, because at input impedance y is equals to L. Y is equals to L. So just I need to put y equals to L here. So this will be the formula of input impedance. What was my characteristic impedance? This was the characteristic impedance. What was my propagation constant? Gamma. Gamma is known as propagation constant. Propagation constant. So what is my propagation constant? Gamma. So that formula also we studied, that was under root R plus j omega L into G plus j omega C, and that can be written as alpha plus j beta. Same as EM wave. What was your alpha? Attenuation constant. What was your beta? Phase constant. So alpha plus j beta, in that manner it can be written. What was your voltage reflection coefficient? This is your voltage reflection coefficient. Not only reflection coefficient, voltage reflection coefficient. So general formula was ZL minus Z0 upon ZL plus Z0. This was at the load, but if I need to write down the complete one, then this will be the formula, minus 2 gamma y. Is that clear to you? And if I need to write down only at load, so that will be equals to ZL minus Z0 upon ZL plus Z0. So this is the summary of the complete lecture that we have studied. Another thing was there about, here I can write down 8th point, that my current reflection coefficient was negative of voltage reflection coefficient. That is the next point. Okay, is that clear? And this voltage reflection coefficient was equals to V0 minus divided by V0 plus. V0 minus divided by V0 plus. Okay, so from here as well, one more point, that V0 minus can be written as gamma voltage reflection but at load into V0 plus. This is how your V0 minus can be written as. So this was also one of the thing. Okay, so these things if you keep in mind, these 2 pages if you keep in mind, then the complete summary is there. What else is the summary? That RLGC, that how will you replace your transmission line. So this is how your transmission line can be replaced. So that's it. This is what we have studied in this particular lecture. Okay, so a very complex topic. It is considered as complex topic, you can ask anyone, but we are going to study it in a very in-depth manner, so that in the examination you don't feel any problem. Okay, and all the formula we have written down from the load. So y is the distance from load. So I hope you enjoyed the first lecture. If you have studied EM wave, then it will be a cakewalk for you, right? So in the next lecture we are going to see that type of transmission line, where we will study lossy, lossless and low loss. These we have already seen in EM wave. This is something new. which is distortion-less transmission line. So about them we are going to study in the next lecture. It will be roughly around 1 hour video only. So in that we will develop some formula, like for different kind of transmission line we will develop the formula of alpha, beta, z naught and deflection coefficient. These formula we will develop, and then that lecture will be completed. So next lecture will be very easy. Some problems also we will solve there. Okay then, so let's meet in the next lecture. I hope you found it helpful, and you can consider liking it and sharing it with your friends. Thank you very much.